to A, not be able to remember formulas on my own, and B, when I make a formula sheet, I end up putting, lots of stuff on it. And so I have the worksheet that I have for you has lots of the formulas and expressions from the three-phase power chapter and the descriptions of what the various things are. And you'll notice here when you look at the Y load and you see that we're going from 0 to negative 120 to negative 240 right here, but up here we're going 0, negative 120, positive 120. Negative 240 and positive 120 are in the same place. And so if you go around negative 240, you end up at the same place as if you go positive 120. And this is going in this order, so with V1 being 0 and then V2 being negative 120 and V3 being negative 240 is the positive phase sequence. But you can switch these and have 0, 120, positive 120, negative 120, and that would be the negative phase sequence. So it can also go in the other direction.
So what's the difference between using either?
Between using what?
Negative 240 or
It seems to me that whenever you're dealing with a network, they use the positive 120, and whenever it's just like a standalone problem, the negative 240 actually seems to be, I don't really see it outside of this book, but that's where I'm seeing it used. So I don't really have another answer for you. I tried to figure that out myself, and I couldn't quite figure it out. But so for example, right here, this first problem, we are given a balanced delta source configuration with a positive phase sequence, and V12 is 208.45 degrees volts RMS, and we need to determine V23, V31, and then what the equivalent Y source voltages would be. And so if we look at our Y source configuration and our delta source configuration, so V12 is the voltage between points 1 and 2, whereas V1 is the voltage between, so that's on your delta configuration. So your delta configuration, you have the voltages between these corners of the triangle, and in your Y configuration you have the voltages between the end of the Y or the star and the neutral point in the middle, and so V1 would be the voltage difference between 1 and the neutral point in the middle. Let me copy this and take it over to OneNote. All right, so this one, we're not talking about a network where we have like a source and a load. We just have this balanced source configuration, And it seems to me that's when they're using the negative 240. So what we're doing with a positive phase sequence, we know that we will be subtracting 120 degrees with each new voltage. So if V12 is 208 angle 45 degrees volts, then V23, it's balanced, so we'll have the same magnitude. So balance has to be 208, and then has to be 45 minus 120. So that'll be minus 75 degrees RMS. And then V31, I'll subtract another 120 from that. Get minus 195 VRMS. So that's part A. I got the phase voltages V23, V23 and V31. And now I need to get V1, 2, and 3 of the equivalent Y. So we know that V1 equals V12 over the square root of 3. So the Y voltage is bigger than the delta voltage by a square root of 3. And so either way you want to think about it, that V1 is the Y is the delta divided by this. Yeah? Okay. If you want to say the Y is the delta divided by the square root of 3, or if you want to say the delta is the Y times the square root of 3. Did I say that backwards? I did say that backwards. I didn't say it backwards. Okay, all right. All right. So so here we'll have V1. The magnitude is going to be 208 divided by the square root of 3. And then our angle is going to be 30 degrees less than our angle on V12. So it'll be 45 minus 30 degrees, and that 30 degrees is, that's always what you're going to do. And so this gives us 120 degrees, angle 15 volts RMS. And then from there, we know, since we're in positive phase sequence, that we can just subtract 120 degrees each time to get the next one. And we know that's not 120 degrees. It's just the 120 degrees shows up so often. I guess I just put a degree symbol there. So it'll be 120. Since it's balanced, it has to have the same magnitude. Subtract 120 from 115 and negative 105. And V3, subtract 120 again and negative 225. And so hopefully you'll have lots of questions like this.
Subtracting 120 degrees twice and then adding it once?
There's no difference.
There's no difference.
Oh, okay.
Yeah.
Like, he's not going to take all points.
I can't imagine why.
Just because he really wants to.
Right.
I can't figure out any reason for it. It was unusual for me to see the minus 240 because I'm used to seeing the plus 120.
Right.
But if I find anything out about that, I'll let y'all know.
Most of what I've seen for the first one's whatever, then it goes minus 120 and then plus 120.
Yeah,
That-
yeah, that's
And
the
they just
whole
leave
I've
it
seen.
at that. So
That's usually the way it's done.
yeah,
Yeah.
that's what I think.
Yeah.
But I think
So
for
this
the
is
first
going
example,
from the triangular three-phase power to the Y three-phase
Correct.
power?
That's correct.
And if it was from Y to the triangle, we would just multiply the square root of 3?
That's right, and add 30.
Yep, okay.
And if it was, do y'all ever deal with negative phase sequence?
I don't think so.
You will when you take power, but if that's just you add 120 rather than subtract 120, which is why is one.
So you can go to and from each of these by just adding, subtract, like this we subtracted, but if we wanted to go back, we would just add.
Yes,
Okay, so.
but we will have more practice with that. So, all right. So now. This is just to kind of help y'all get a feel for these things. So when y'all took circuits 1, did y'all do delta Y transformations? Okay.
I don't think we did anything, so I don't think we did.
Okay, all right, so one of these is Y, so I guess we should start with that. One of these is Y, also called star, if you ever hear star. One of these, and also, which one is called pi? This one, okay, delta is also sometimes called pi because if I wanted to, I could kind of make it look like a pie. Anyway, I think I have that right, that's the one that they also, but anyway. So the Y is the one that looks like a Y, and the delta is the one that looks like the Greek letter delta. So this is the Y, and this is the delta. And our first job is to, on these, to label phase voltage, phase current, line current, so that we can see what it is we're talking about when we are doing these things. So I'm going to start with the delta, and I'm going to draw it just slightly differently in a way that's going to make it easy for me to label it. So I still have the lines that are coming from each vertex here, and I can call this phase A, phase B, phase C, and if I wanted to talk about V phase, V phase is the phase across one of these inductors here, and V line is the voltage between lines, and I line is the current through one of those lines. Line voltage, phase current, so the and the line current, so the phase current would be the current in one of these, so that would be the phase current. For the delta. Now I'll draw a Y. And again, I'm going to draw it slightly differently. The Y has a neutral point right there, that's N for neutral. And to just demonstrate that, I'll put it like ground. Now, if you have a balanced circuit, it should be 0 there anyway, so you don't officially have to have a neutral line there. Okay, and here, so that's a Y. So you can see this tail that I have right here is, kind of equivalent to that one. And for a Y circuit, the I line equals I phase. And you can see how that's true because it's the same current going through the line as going through the phase right there. V phase is right here. V line is the voltage between the lines. And that equals the square root of 3 V phase. So the V line is square root of 3 V phase, but the currents are the same. Now in the delta, V line is the same as V phase. If you just look at this, the voltage between here and here has to be the same as the voltage between here and here. So in the delta, it's the voltages that are the same and the currents that are different. And in the Y, the currents are the same, but the voltages are different. And let's see if I had anything else to say on that one. If I did, I didn't write it down, so. I did have something else. Nope, I did not. Okay, so I'll just write them out, what I said. I'm just going to write them out. That I phase equals I line for a Y configuration. And V phase is less than V line in a Y configuration. And then in a delta configuration, I phase is less than I line, and V phase equals V line. All right, any questions on that? And anytime there's going to be a difference like this, we know it's going to be a square root of 3. So if I phase is less than I line, then I line is going to be square root of 3 times I phase. Yeah.
If you're multiplying by root 3, wouldn't it be more? Wouldn't it be greater than 0? For the y configuration, it's v line is equal to 3. Oh wait.
Yeah. 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 Okay. All right. Any other questions? All right. Moving on. All right, so this one should be easy now. In a balanced Y-connected power system, calculate the phase voltage. By the way, the place I got this from is using E instead of V, so whenever you see E, that's V. V phase if V line is 480 volts. Okay, so based on what we just did on a Y-connected power system, what should it be? So I want everybody to see if you can come up with the answer. What's that?
480 divided by square root.
That's it? Yep. So it's going to be 480 divided by square root 3, which gives us 277 volts. You're probably not going to have too many questions like that. Okay, so now, but something like this, maybe. So I've got a network, so it's a delta-delta network, so you can have delta-delta, y-y, delta-y, y-delta, with one side the source and the other side the load. Yes?
Scroll up just a bit and get that last.
Yes.
Ah.
It's really good, I found, to spend some time with these and kind of come up with your own way of reminding yourself when there's the relationship with the square root of 3, which one is bigger, and so that way you'll know whether you should be multiplying or dividing. Okay, so we need to calculate all voltages, currents, and total power in this delta-delta system. And so which things do we know are going to be the same? And once we have one, we have the other one. So, so if we look at the source and the load and how they're connected to each other, we can see that those voltages have to be the same. And so the phase voltage of the source has to equal the phase voltage of the load. Now, do we know the phase voltage of the source? It's 230. That's the one that's given. Now, right one? Yes, it is. Okay, so now let's see if we can find our phase current on the load. So, all right. So on the load, we have that our current Oh, I get myself messed up because L is line, not load. I was like, but that's not right. Okay, so I phase is going to equal our voltage divided by our resistance, which is 4.6 amps. Now, is in delta, is our line current the same as our phase current? No, is it bigger or smaller? The square root of 3 times. It's bigger. And so our line current is going to be the square root of 3 times 4.6 amps, which is 7.967 amps. So this was 4.6. This is 7.967. And we know that this also has to be 230 volts because we know that for the delta, the line voltage is the same as the phase voltage. And on the source, our current is going to be the same in our source as the phase current in the source is the same as the phase current in the load. So that will also be 4.6 amps. And our total power, if we go and look here, should end up being the same. it's going to be 3 I squared R. I'm not seeing that on here anywhere, but it's what you would get by combining
Is that IL squared?
just it is phase squared. I phase squared R. Well, it has to be, because if we look at our circuit, what kind of power are we talking about? I mean, it's the power from these 3 resistors right here in the load. And you know, what is the power for a resistor? It's I squared R. I mean, you could use any of your different power formulas to come up with it, and there's 3 of them. And so our total power is 3 I phase squared R, and it's phase because it's within the phase there. And so that's 3 times 4.6 squared times 50, which is 3,174 watts. And that should be the same answer that you get if you computed it any other way, but to me the easiest way to see it is just to look at it and say, okay, well, the power is going to be the power dissipated in the load.
That's the delta equation.
What's that?
That's a delta equation.
Yes.
And the other one that you had would be just a y.
I think the one I was just looking at was a Y one. Yeah.
So the I phase is the V phase over the load.
Yes. Yeah, it messes me up that load and line both start with L, but yes. So it literally is just the current across that little thing right there. Okay, so questions on that before we look at our next one? And by the time we get to the last one, we'll see how they all work. We just did delta delta, right? Okay, so now we'll do y y. So what's the same in y? Current. Okay, so if you look at the way this is drawn here, we've got the 13.8 kilovolt is drawn showing between I'll make these V's. Is between the 2 lines. So that's V line. So that is 13.8 kilovolts. And we know that the phase voltage in the source, so the phase voltage is going to be the line voltage divided by the square root of 3. Or 13.8 kilovolts divided by the square root of 3. And that gets 7.967 kilovolts. Now, our source and our load are completely symmetric to each other, and so we should have, if this is the voltage, the phase voltage on the source, it should be the same as the phase voltage on the load. So that will be 7.967 kilovolts. So now that we know what the phase voltage is, we can find the phase current. And so the phase current will be the phase voltage over 1.5 kiloohms. So that would be 7.967 kilovolts over 1.5 kiloohms, which is 5.312 amps. And now, since our load and source are symmetric, we should have the same phase current in the source as in the load. So that should be 5.312 amps. And because it is a Y network, our line should be the same as the phase current. So 5.312 amps for the line. And then our power, looks like did I complete that? So there are a couple ways to do it, and I think I'll do it same way I did the last one, because the power has to be the power in these 3 resistors, and so I'll have 3 times, and I have the voltage and the current on each of those resistors. So the voltage across each resistor is 7.967 kilovolts, and the current on each one is 5.312 amps, and that ends up being 127 kilowatts. But just to see that we could do that another way, we have these 2 things. We have that the total power equals the square root of 3 VL IL cosine phi, and we have that it is also 3 V phase I phase cosine phi. Now, the reason our voltage and our current are both at angle 0, and so phi is just 0, so cosine phi for these is just 1, and so for these cosine phi is just 1. And if you were to we essentially just did this. If you were to do the line voltage times the line current and multiply it by the square root of 3, you should get the same answer. Yes?
So, depending on like what the question asks, like if it asks for like what power the source is, we would use VL of the source, IL of the source, or V phase of the source, I phase of the source. because they both have their own. I mean, in this one it's the same.
Well, shouldn't they be the same? I mean,
Are they not? Are they always the same?
should be. I mean, I think.
So they.
Well, okay, total. So like, the total power supplied has to equal the total power absorbed. And so our source is doing the supplying and our load is doing the absorbing. Now, if I'm looking at, if it's not balanced, and I mean, and the ones we've got here are nice and symmetric, and so I guess it could be different, and I haven't played around with enough recently to be able to answer that question very smartly.
Okay.
So I could make something up, but I would just be making it up. But I can do that. Yes?
One of the things that he said in class was that he wants us to focus on doing YY configurations.
Oh, okay.
If we're given a delta, he wants us to convert it, or he tells us we should convert it to Y and then use just the math for YY.
Okay.
I don't know how much that really changes, but it was something he said. He said
I think so. I don't think I can't imagine he would not give you balanced. That would,
math was really nice.
yeah.
Other than it's like that's great.
I will keep that in mind as I go forward here. I was hesitant to do that because like I asked y'all, I was pretty sure like if y'all had done a whole lot of delta Y conversions like before now, and the answer was no, and so I was kind of thinking not to muddy things up by doing conversions when I didn't have to, but we'll see because I'm not really sure where I'm going from here. But that might mean that I don't do the next two and instead skip ahead. Let me see what I think about that. So this one is a delta Y, and this one is a Y delta. But in one of your examples, didn't he do a delta delta in one of your examples?
He did, but he had us convert it, told us to convert it to YY.
Okay, since I did not work these others out that way, I don't want to do it without having my answers because I want to make sure that I have the right ones. I'm going to skip ahead to the one that I have that is YY, and then I'll make sure that I redo the ones a different way. So I'm going to skip all the way ahead to and I'm going to stop this for right now and save it, and then I'm going to come back, and then we're going to do the last problem on here that has a power factor compensation, but now with Y source and load. So hold on.